The benefits of science will be even more spectacular than we can ever imagine. I wanted to do something that is of long-range benefit to humankind. Practically everything we touch in our daily lives has been developed and improved through basic research. Science is taking us on an ever-accelerating journey into the future.
Please welcome to the stage 2025 ACS President Dorothy Phillips.
Good evening, everyone. I am Dorothy Phillips, 2025 President of the American Chemical Society. It is my sincere pleasure to welcome you to the ACS Spring 2025 Lecture Series sponsored by the Kavli Foundation. ACS is deeply grateful to the Kavli Foundation for enabling us to highlight the achievements of outstanding researchers in the chemical sciences through this lecture series. This program supports goals that ACS and the Kavli Foundation share to advance science for the benefit of humanity, promote public understanding of scientific research, and support scientists in their important work. The Kavli Emerging Leader in Chemistry Lectures spotlights exceptional early career scientists under 40 who have already made outstanding contributions to scientific engineering research. Tonight, we have the privilege of hearing from one such visionary leader. It is my honor to introduce Dr. Nicholas Jackson, Assistant Professor at the University of Illinois, Urbana-Champaign, and a leader of the ACLD AI for Materials Group at the Beckman Institute for Advanced Science and Technology. He has received many honors, including most recently the Cottrell Scholar Award, the AICHE Computational Molecular Science and Engineering Forum Young Investigators Award, and the ACS Open Eye Cadence Outstanding Junior Faculty Award in Computational Chemistry. Dr. Jackson's research group works on problems at the interface of soft materials, quantum mechanics, and machine learning. More specifically, they focus on coarse-grained electronic structure methods, conjugated materials theory, and sustainable polymer design. Dr. Jackson's work has been widely recognized for its pioneering integration of statistics, programming, and machine learning in the chemistry enterprise. This evening, Dr. Jackson will share the latest development in AI-driven modeling of electronic processes and soft materials in his lecture titled, A Quantum Mechanical Frontier for Polymer Science. Everyone, Dr. Nicholas Jackson.
Okay, thank you very much. It is an incredible and humbling honor to be here giving this talk. So I will do my very best to give you an entertaining story tonight. So I'm going to talk about what I think is a new emerging frontier of polymer science that involves the quantum mechanical world as opposed to the purely classical one. And I think that we're going to see a lot of these topics emerging in the near future. So I'll dive right in. The thing that motivates the majority of what I and my group study are the fact that the synthetic polymers of today are not that great, right? We're all familiar with the news flashes that come up periodically. There's all the plastics in the ocean that won't degrade over any reasonable time. Making these plastics requires a truly incredible amount of the US energy stockpile of the fuel resources. And you're starting to see these emerging studies about microplastics and the negative health consequences that they can have on our society. And so what motivates us is that, these things are bad and we need to fix them. And so how can we use computation and AI-driven design to try to make a better future with these materials? This is not to say that all polymers, by definition, are bad. Biology is rife with great polymers that have incredible function, are sustainable, degradable. You see things like DNA, proteins, lignin, natural rubber, mucus. So we know that it's possible. We know that we can make polymers that behave very well, that sustainably degrade, but we are not there just as of yet. So when I think about what the future might hold for polymer science, here is a subselection of the, I would say, important problems that our society faces right now. You have, how do we make clean and cheap water? How do we harvest cheap and clean energy? How can we live better and longer? How do we address waste? And how do we travel to other planets, if that is of your personal interest? There is tremendous progress in all of these areas that the community has built upon. So you'll find polymer-based water filtration, photovoltaics, bioelectronics, new recycling and upcycling strategies, and even new polymer composites that resist cosmic rays as you travel through space. What I am here today to argue, one of the main thesis topics here, is that if you think about the underlying physical chemical processes that govern the solutions, the potential solutions in each of these areas, you'll see things like photoreactivity, chemical degradation. You'll see things like electron and exciton transport, chemical stability, photostability. You'll see things like charge carrier doping, electronic species. You'll see things like chemical, thermal, and photostability as it relates to polymer recycling and degradation, and even radiation degradation and static charging. Point number one I'd like you to take home from this talk is that the majority of the problems facing polymer design, the design of new synthetic better polymers, I would argue are fundamentally quantum mechanical in nature. So this is in contrast to the architecture of theoretical design for polymers to date, I would argue. There have been an enormous number of brilliant theories and computational works in designing polymers as we know them, but they have been predominantly classical. Whoops. predominantly classical, in that you're trying to predict structural, thermodynamic, or mechanical properties. If you look at this, subsampling of cool problems at the frontier of polymer science, I would argue, as I did on the previous slide, that the majority of these require some sort of quantum mechanical modeling to really make rational design and understanding a reality for these material classes. So not only is the point number one of this talk, we need quantum mechanics to solve today's problems, but it is, what are the actual tools we need to get those jobs done? What I'm going to tell you about today are two stories. First story is going to be primarily modeling driven. The second story is going to be a close-knit collaboration with experimentalists. Both of these are going to cover the main topic that my lab is trying to push forward, the frontier of how you design quantum mechanical properties in polymers. So reactivity, charge conductivity, excited states, those are the things we want to learn, and we're going to bring to bear on this two separate categories of tools, being AI-driven electronic structure predictions. How can we get to really large length scales, the characteristic of soft materials? We're going to talk about electronic conductivity in particular, and then we're going to talk about how we design a photostable polymer or organic molecule, which is, despite the simplicity of that statement, a shockingly hard thing to do. So in telling you about story one, how do we use AI to basically accelerate and advance our ability to perform quantum mechanical design in new polymers? I first have to tell you something about a coarse-grained model. My group does a modeling technique called coarse graining. What that means, for those of you who haven't heard this, if you're familiar with methods like quantum chemistry or density functional calculations, these are things like Gaussian or VASP or quantum espresso. These models require that you specify all of the atoms, all of their locations, and all of the electronic detail. Basically, in order to understand a molecule, you need to specify every degree of freedom in that molecule. This is not the only way that modeling of materials and chemistry can proceed. Coarse-grained modeling is basically just, we don't need to keep track of all of those details for every property that we're interested in modeling. So if you've ever seen things like the Martini coarse-grained model or continuum finite element methods or pseudo-potentials, these are all methods that can model chemistries and materials that basically are agnostic to the underlying chemical structure. You fit parameters. So what my group focuses on are coarse-grained modeling methods capable of describing quantum mechanical effects. Before I tell you about the latest and greatest of what we think the future is here, I'm first going to put up the comparison for how we do this right now. So if you look at the state of the art for electronic structure modeling in soft materials and polymers and disordered polymeric systems, the general strategy is you want to simulate structure. So you go and you get an atomistic MD simulation or some big supercomputer and you watch the polymers jiggle around and reach some energy minimum. But usually it's too expensive. The length scales you have to simulate and the time scales you have to simulate are just too large to spend on atomistic modeling. So you make a coarse-grained model. So here is a coarse-grained model. On the left is a bithiophene. Here is a model in which I have just forgotten about certain nuclear degrees of freedom. It still sort of looks vaguely like bithiophene, but it is coarse-grained in that I've eliminated some unessential degrees of freedom. So usually what you do is you take one of these, you simulate the structure of the system with the coarse-grained model. It's faster, it's bigger, because there's fewer things to keep track of. And then what you do is you need to basically take this, if you're interested in electronic structure, and you need to solve the Schrödinger equation, right? If we have the molecular structure, if we want electronic properties, we have to solve the Schrödinger equation. There's no way about it. No other way about it. If you've thrown out some of the atoms, how can you possibly solve the molecular Schrödinger equation? And so this is a very fundamental challenge in modeling of these materials. And what you end up doing typically is you do a big coarse-grained simulation that lets you simulate a really, really big polymer system. What you then do is something called backmapping, where you basically just put in all of the degrees of freedom you deleted in the first place, just so all the molecular detail is there. And then you run a whole lot of DFT calculations to try to build up the electronic structure of the system. And it's critical to note that soft materials are disordered. So if you've ever been used to like putting a crystal structure into VASP or quantum espresso and getting out a band structure, you can't really do that here because the length scales are on the order of tens, hundreds of nanometers. They're heterogeneous, and there's many, many different conformations and many, many different morphologies that contribute to the ultimate physical property that you're trying to predict. So this ends up being an incredibly expensive strategy. To tell you just how expensive it is, here is a box simulated from a former postdoc in my group. It is about 10 meters on a side. It has 1,200 molecules of this thing in it. Pretty small box in the grand scheme of things. If I want to capture the electronic structure necessary to describe electronic conductivity or reactivity or photostability in this, the cheapest possible version of this calculation that I can do for one thermodynamic state point, one chemistry, one thermodynamic state point, is going to cost me about 10 to the 5 service units on a computational cluster. To give you a sense of how much computational cost that is, if you go to the biggest DOE supercomputers in the country and you request a massive allocation, you'll usually get about 10 to the 6 and usually 10 to the 5. So what this means is that to study the electronic properties of one molecule at one thermodynamic state point, you have to go shell out for a leadership class supercomputer. Obviously, this is not a robust strategy for understanding and designing molecular materials. So this is why we have such a poor understanding of electronic properties in soft materials. What's the potential solution? The fundamental idea that my group works on is the following. Let's imagine that here is the atomistic model. So this is the molecular model of my system with all the degrees of freedom. If I had infinite computational power, I could just call out and solve the Schrödinger equation for a really big box, and I just don't worry about the computational cost. What we propose to do is we coarse grain the system, so we systematically delete or average over degrees of freedom. So this goes from 4 atoms to 2 effective atoms now. So here's our coarse grain system. You can simulate bigger scales. It's cheaper. And what we want to do is we want to develop methods that do this. That solve something that looks like the Schrödinger equation, but only using the coarse grain degrees of freedom. So little r is all the atomistic degrees of freedom, all the coordinates of all the nuclei. Big R is these coarse grain particles, and we want a method that does that directly. If you do that, you don't have to do back mapping, you don't have the multi-scale workflow, you don't have ad nauseum quantum chemistry, you don't have this enormous computational cost. In reality, as I'll show here, it amounts to about a factor of 10 to the 6 acceleration of any kind of computational design of a quantum mechanical property in a soft material. For those of you interested in a little bit of the technical details, just a smidge, the fundamental challenge here is we need to learn how to predict distributions of properties from coarse grain configurations as opposed to single properties. So the example here is a molecule that's jiggling around. I'm interested in some molecular orbital energy as it's jiggling around, and I sample a bunch of different independent configurations, and every time I sample one, I will get a different manifestation of what the energy level might be. At the coarse grain resolution, this structure up here has averaged over a lot of this detail. So in reality, what you have to do is you have to predict a distribution function as a function of the coarse grain configuration as opposed to a single value. This is a very fundamental difference in modeling electronic structure at a coarse grain resolution. It's incredibly challenging to do, but what we use to make this happen is basically state-of-the-art machine learning algorithms. And as I talk about these results moving forward, when I say that I'm learning electronic properties, specifically what I'm learning are how the highest occupied molecular orbital energies and the highest occupied molecular orbital couplings between dimers, how those vary as a function of the coarse grain configuration. So I said we have to learn distribution functions. I'm a methods person. So the first thing we have to do is we have to make sure that this proposed coarse-grained electronic structure prediction is going to match up to the full expensive DFT thing that you would have to do. What we do is we take this molecule and other ones, we look at its motion, we take the two principal components of its motion and a trajectory, an MD trajectory, we look at spots in these components of its motion, and around each of these spots, you will see that there is a distribution of electronic structure. This is why I said before, we have to learn distributions of electronic structure throughout the configuration space of the molecule. And the short version of this is that using these state-of-the-art methods, we can match these distributions almost quantitatively throughout all space for basically any molecule that we've come across to date. And so what this means is that we can predict something like a molecular orbital energy or a charge density purely from the coarse-grained resolution without having to call back to the atomistic representation. That's a pretty cool thing, in my opinion. It is fundamentally important because it enables this bypassing of having to run exclusively through expensive atomistic models. If you want to get a little more into the details, what we actually do is we run purely coarse-grained simulations of structure. So we do like a big coarse-grained simulation of polymers packing in a box. We then call out to our electronically coarse-grained model to predict the electronic structure within that box. And the entire molecularly specific electronic structure of this system happens at the coarse-grained resolution. There is a small training set that basically fine-tunes what the coarse-grained electronic structure should be, but all of this proceeds without having to ever think about all of the atoms ever again in your workflow. And as I said before, the critical feature here is that this is about a 10 to the 6 speed up. Now, if you have gotten down the rabbit hole of thinking about this coarse graining idea, which is a fun exercise for sure, you can start to ask, okay, so I've heard that if I have a coarse grain representation, that you can use these machine learning methods, whatever they may be, to predict the electronic structure of the system. Cool. That does not answer how the heck you pick the coarse grain representation in the first place. So here is a molecule with its orbitals in all of its glory, all of the information. Here is a coarse grain version. You could say, well, it's all right. It probably has a lot of the information, albeit not all of it. And then you could also do the physicist spherical cow thing. Here is a sphere to represent my molecule. Everyone in this room's blood pressure just went up probably because of this representation. But, right, this is the regime of how you could represent a molecule. You could not predict the electronic structure if you treat your molecule as a sphere. So how you pick the coarse grain representation is really fundamental to how successful this whole strategy can be. The naive way to do this is to just train a bunch of these coarse-grained electronic prediction models on a bunch of different representations. So you dream up whatever representation you think might be cool. You then evaluate how much error it has. So here what we've done is we've taken the same bithiophenol molecule. We start with a bunch of coarse-grained beads, and then we basically decrease the resolution all the way down to just 4 beads. As you're deleting information in the molecule, the error has to go up. You're trying to make a prediction without all of the knowledge of the nuclei. Curiously, when you hit this point in representation where you go from 6 beads to 4, your error spikes up mysteriously. So it doesn't just get worse, it gets dramatically worse at a particular resolution. This tells you, if you go into the weeds, that you have lost the interring dihedral degree of freedom here. What that means is the pi electronic structure of a pi conjugated dimer depends dramatically on what the overlap of those 2 p orbitals on the neighboring carbons are doing. So as they rotate, you go from total overlap to none. That really affects the pi electron system energy levels. And what this tells you is that, well, when you go from this resolution to this resolution, you can't really describe that transition anymore, so your model now becomes pretty bad at its job. So this is again, I said a naive kind of brute force way, but you can actually use machine learning and coarse grain to develop intuition to molecular systems about what degrees of freedom are controlling the electronic structure variations. Of course, that is not an elegant solution. An elegant solution would be to come to a computer and say, I have a molecule, I want to predict this thing, I want to use this many beads, coarse grain beads. Show me what the best possible representation in the world would be. We also attempted to do that. It's a very challenging task, and it involves a lot of the state-of-the-art developments in message passing, graph neural networks, and AI. But my student, Charlie, who's a brilliant student, developed this method that basically lets you take as input a small set of quantum chemistry data and MD for a molecule, and the AI algorithm basically does the electronic structure prediction, but as it's doing it, it's basically turning on and off different atoms and seeing what atoms it can and cannot turn off to affect the prediction task quality. And it learns an optimal representation this way all by itself. So what this manifests in terms of actual detail, here's our molecule that flops around and the electronic structure varies. What we're going to do now is we're going to apply that algorithm to systematically coarsen this molecule. So what I have here on the y-axis is the number of coarse-grained beads I'm going to use, and on the x-axis is the indices of the atoms. So as I coarsen the representation, as I go up, these highlights in the color bar show me what numbers of atoms it's deleting as thinking that are not important. The first thing to go, the side chain. sp3 carbons attached to a pi system, the 0th order, those aren't going to do a lot of work. As you go up and you further coarsen, you start to get some more complex correlations. But the basic point of this is that we can input a molecule and we can output the best possible coarse grain representation for the prediction task. So this really helps us get our foot through the door in practicality in terms of a new modeling paradigm for electronic structure and molecular systems. Okay, what I've showed you now, or what I've showed you up to this point, are basically characterizations of little molecules. And I motivated this whole talk by saying we're going to get to these really big length scales and we're going to simulate these really complicated properties. I have always loved liquid crystals. If you don't know what liquid crystals are, they are liquids that have some crystalline character to them. They have some order to them beyond a normal isotropic liquid. For example, if you have a thermotropic liquid crystal, as you cool it down, you can take it from a disordered liquid to all these various states of order. These are all still liquids all the way to the crystal. What I've always wanted to do for literally a decade is to try to predict electronic conductivity in a semiconducting system as you transition the molecule through all of these points. The reason this is a cool test problem, if I was to do this with existing resources, I would be writing 1, 2, 3, 4, 5 supercomputing allocations to the DOE. I don't have time for that. So what we do to set out to try to tackle this, we pick a molecule that's an important molecule in the electronic transistor community. It has well-defined field effect mobilities. It has well-defined liquid crystalline transitions. And what we want to do is we want to try to predict the experimental values of the mobility using this entirely coarse-grained novel prediction capability. If we can do that, maybe we're onto something. If you want some details, if you've ever liked the modeling details, this is effectively what we do. We make a coarse-grained model using something called iterative Boltzmann inversion. We then have a small training set of electronic structure data. We featurize it for the machine learning. So here we featurize it as the distance matrix of the coarse-grained bead positions. We then train a complicated or a fancy neural network to predict the distribution of electronic properties. And this pipes to what are electronic Hamiltonians, or just simply characterizations, quantitative characterizations of a system's electronic structure. And we can use these to compute any electronic observable that we're interested in. Does it work? On the right here, I have the computed electronic mobilities in 3 of the phases. I have the field effect transistor mobilities scaled down to the appropriate charge carrier limit. You see that our method, which is entirely coarse-grained, entirely bottom-up, purely coarse-grained electronic structure, purely coarse-grained structural prediction of liquid crystals, hits these semi-quantitatively. If they hit them quantitatively, honestly, it would be a little worrying because you're comparing a device scale measurement with a lot of noise on it to a small molecular modeling system. But the critical feature here is that to generate this data with the conventional approach would take approximately 8 times 10 to the 7 CPU hours. We do ours with 107 CPU hours on our home little computing cluster in Illinois. So what this lets us do now is take a polymer or a soft material and compute its electronic structure and compute its electronic properties. This could be substituted. We could be trying to do reactivity or degradation or excitation transport. And we can do it with 107 hours on a CPU. Of course, there's a little overhead, but it's still 5 orders of magnitude less than the state of the art. That's what we're excited about. You can take this to polymers. So I showed you liquid crystals. You can take this to polymers. Here are some conjugated polythiophene at the coarse grain resolution. On the left, they're in a good solvent, so they're happily solvated, they're extended, they're flopping around. You change the solvent to be poor solvent quality. What do? They aggregate, they form fibers. These pi systems stack on top of each other and flatten out into these big fibrous rods. If you look with our electronically coarse grain method at what the molecular orbitals are doing, so here we're showing like the top 10 highest energy molecular orbitals, and same thing here. Black means there's a high density of that electron. What you can see is in this transition between morphologies, these wave functions, these electron carriers, love to flatten out along the chains, and they love to delocalize across multiple chains. What this lets you do, again, is actually try to model how processing influences structure and thus electronic properties in soft materials and polymers. You can also connect this right up to a mobility estimate. So if you're interested in the electronic conductivities, the electronic mobilities of these systems as a function of processing, as a function of solvent, as a function of chemical structure, you can hook these up and generate these estimates quite rapidly. If this sounds pretty good, there's always a thing to be improved. This is all for a single chemistry. The methods I've talked about are targeted towards modeling single chemistries at very large length scales as a function of processing conditions and morphology. What if we could have a chemically transferable model? Gaussian is incredibly useful because you draw a molecule in a box and out pops the electronic structure. GROMACS is useful because you draw a protein and you run the simulation. What we'd love to have is a chemically transferable model like I've described here. There are classes of these for traditional coarse grain modeling that are incredibly successful. So Professor Merrick and Groningen has pushed this Martini model for a number of decades. It's incredibly powerful, and it lets you simulate structure formation at coarse grain resolutions across a broad chemical space. So really what we're excited about moving forward is, can we make a model like this that's electronically coarse grained that operates across a broad swath of chemical space? There are a lot of issues to be tackled. One that is critically important is, where on earth are you going to get all of that training data from? This is all machine learning based. It has to learn from something. This is a plug for a thing in my group that's slightly orthogonal to what I'm talking about, but it is the source of a lot of the data we use to train our models. This is called the Open Macromolecular Genome, or the OMG. The Open Macromolecular Genome is a database of about 12 million synthetically feasible polymers. Synthetically feasible meaning an organic chemist would not laugh if they saw the structures that the AI proposed. And what these contain are 25 different properties, ranging from electronic properties to chain stiffness, to Flory-Huggins parameters, to log P estimations. And so what we would love for the community to start to do is to start contributing and pushing forward an open polymer property database. Again, I said this is a little orthogonal, but this is something that's really lacking in the community for soft materials development. I would also say that we have a lot of these properties all calibrated to their experimental analogs. So it's not just, computational models exclusively. They're all calibrated to the associated experiments. I say that just as you need data to train a chemically transferable model, so that's where we get it from. As a test of if this is feasible for what we want to do, we've tried to make a chemically transferable model over a small chemical space. Here we have sequence-defined polythiophene with 25 different monomers according to these substitutions. And what we're trying to do is to learn one model that can predict the electronic structure at a coarse-grained resolution across this entire chemical space of lengths and sequences. As it turns out, it does a pretty good job overseeing sequences in the training data, and even when you extend it to sequences outside of the training data, it still does semi-quantitatively quite an outstanding job. This is just a proof of principle that you can actually potentially do this moving forward. There's a ton of work we have to do, and there's a ton of I's and T's that need to be dotted and crossed. But in principle, we are optimistic that we will be able to push models that can do these rapid electronically coarse-grained predictions across a broad swath of chemistry without having to get into the weeds of the models every time. Okay, I'm now going to switch to something that is a experimental collaboration. So it still follows the theme of we're trying to design quantum mechanical properties and soft materials and polymers. But in some cases, modeling just does not have a solution. And one of those things it does not have a solution for is in modeling photoreactivity and photostability. The people out there who can do this do it for small, chemically specific systems, and it is incredibly computationally expensive. So if I want to understand how to design photostable molecules across chemical space, computation can't help me. Experiment is expensive. So we're going to do a close-knit collaboration that's AI-driven to try to both design and understand photostability in organic molecules. One of the reasons we picked photostability, if I think about these grand challenges and I think about their solutions and I think about these things that popped up here as the physical mechanisms, photostability is basically important for anything you do not in the dark, right? If you are doing any chemistry of any kind in the light, you have to worry about if you're photodegrading. And so with that in mind, it's kind of a shock that we don't know general rules for predicting it. I would argue that there are few, if any, broad-ranging chemical design rules for photostability. The asterisk here is if you go into the carotenoid literature of photosynthetic complexes, they've done a lot of work on carotenoids to understand it. But if I ask about general chemical space, you will come up short of satisfying answers to this question. The context we want to push this forward in is in solar cell design, organic photovoltaics. I can summarize the field right now, perhaps not too coarsely, by saying a lot of brilliant chemists have allowed us to make really high-performing solar cells, but it's still really hard to make ones that are high-performing and stable over a long period of time. As I said before, the experiments and simulations are very challenging. So what we want to do is we want to hook up AI and computation to experimental campaigns to try to collect experimental data across a broad swath of chemical space as efficiently as we can. I was incredibly fortunate when I started my career at Illinois to come into contact with these four amazing people, Charles Schroeder, Ying Zhao, Marty Burke, and Alanis Buruguzik, in which we've constructed this tight-knit, data-driven collaboration for understanding photostability. This work is entirely a team effort, This is a complicated picture of what we actually did. I'll take you through it step by step. In the first phase of this experimental campaign, what we did, we said, okay, we want to understand how photostability works broadly across chemical space. So what we're going to do is we're going to use Bayesian optimization to suggest chemistries that it thinks will be more photostable. We're then going to use the automated synthesis capabilities of the Burke and Schroeder labs to rapidly synthesize these new molecules. We will then use the characterization capabilities of the Zhao lab to characterize the photostability. Those measurements will come back into the Jackson lab, and we will suggest new chemistries moving forward that we think will optimize photostability. To be concrete, our optimization goal is the product of the spectral overlap and the lifetime of a molecule. Why the product? The easiest way to make a molecule last forever under illumination, make it not absorb. What we do, we define a diverse chemical space of 2,200 possible molecules, originally down selected from like millions, according to this donor bridge acceptor concept. We then loop through these synthesis and characterization of absorption spectra and lifetimes. We are feeding the AI algorithm at every step essential DFT-derived, quantum chemistry-derived information about its ground state and excited state electronic structure. It's not the lifetime in itself, but it is information. And then we loop this around and we just repeat and we just let the AI guide it. This is truly the most anxiety-inducing collaborative experience of my life because as an AI person, you're sitting there saying, I want you to go make and measure those 6 molecules, and then they go and they actually do it. Right? You're putting the reins of this optimization in the hands of the AI. Does it work? It does. If you run this campaign over 5 rounds, so here is the first batch in blue of chemistries that are sampled, and then in each round, as the AI is learning what molecules it thinks will be more photostable, they start to inch up more and more towards this frontier of high photostability and high spectral overlap. The champion molecules that come out of these campaigns are the following. They're heavily laden with thiophene-based chemistries, which is probably one reason why those proliferate a lot of the organic semiconductor literature. And if you look at actually how efficiently they find these high photostability chemistries, so here is how photostable of a molecule we find as a function of how many molecules we've synthesized. It dramatically spikes up in just tens of molecules. This is really cool because we have done a local optimization of photostability across a chemical space of about 2,200 possible molecules, and we've managed to do this by only synthesizing and measuring 1.5% of the chemical space. If you have been hesitant to use Bayesian optimization or AI to guide design campaigns to date, do not be hesitant. It will work. I will basically promise you. This is a task that we had literally no insight into. We do not have general design rules. We just put it in the hands of the optimization algorithm and let it go, and it led us to this. It's really, really incredible. One thing that we can do that's really helpful is we can track what our AI algorithms are doing as the rounds progress. So on the top here are just a bunch of things that the AI is using to try to figure out how photostability works, a bunch of the features. And on the y-axis here is the round that we're going through. And you can see that in the initial phases, it's not quite sure what to use to predict photostability. But as you get towards the end, it really hones in on some feature right here. When we dive into the statistical analysis of what it actually was using to predict photostability, here we have looked at basically how accurately we can predict the experimental photostabilities as a function of all the different pairs of features of the molecule that we could use to try to make a prediction. You could see that different features light up corresponding to high predictive capability, and in particular, the triplet density of states of a molecule, basically what the energy levels of the excited triplet states of a molecule are, correlate really strongly with the photostability that's observed across a really broad chemical space. In fact, if you use the metric of the the low sliding excited state triplet energy that is drawn from the carotenoid literature as being the determinant of photostability in carotenoids, our features that the AI has extracted are actually statistically more predictive than the one design rule from the carotenoid literature. In particular, it's the triplet density of states at high energy of the molecule, which when we heard this, we were just completely baffled by. We spent a couple months just basically not believing it and trying to rationalize how this could be the feature that predicts photostability across a broad swath of organic chemical space. With that in mind, and not believing it, we basically said, all right, we're going to put it to the test. The AI generated basically a hypothesis or an idea as to what controls photostability. I'm going to create a validation set, and I'm going to force it to predict on the validation set and prove that it knows what it's doing. So what we did was we used our AI model with this triplet density of states as the understanding of what predicts photostability. We then predicted photostabilities across the entire 2,200 chemical space. And then we batched these into groups of high performers and low performers. And we said, okay, here is a batch of 7 high performers that should be predicted, and here is a batch of 7 low performers that are predicted. We're not just going to see how well the model can predict the high photostability, we're going to see how well the model can predict the relative ordering and the ranges of the photostability for these molecules. And if it can do that, then I have a lot more belief that this triplet density of states it found is a determining factor. This is the second most anxiety-inducing slide of the collaboration. Here are the 7 molecules that were predicted as the high performers. Here are the 7 molecules that were predicted as the low performers. If you look at all of them, here on the left, generally high. Here on the right, generally low. If you p-value them with the appropriate statistical test, it's statistically significant. If you have eyes in this room, you're looking at the thing right here. What is that about? In the bottom 7 set of proposed molecules, we find the highest performer of all. That's not great. We dove into the details. If you look at the triplet density of states here, you will see that the triplet density of states of this outlier molecule are very unlike any of the others. These are all the other molecules that the model had seen. Is very unlike the triplet density of states that it had seen to date. If you go into the literature and you look at this anthraquinone, which it had not seen before, you find out that this is actually a fabulous triplet state quencher in the fluorescent molecules literature. And so what this is here to tell you is that when you're operating with a Bayesian optimization or an AI-driven campaign and you're in the low data limit, you will always have failures. Just like a graduate student or a professor learning a topic for the first time will have terrible failures in trying to understand something as they start. We like to call these knowledge generators. It's the positive spin on failures. But to miss out on things early on is a normal component of trying to understand. The really cool thing that happens is what we were worried about is when we retrained all our models with the new outlier and all this data, we were like, oh no, it's going to come up with another feature and this whole thing has been for nothing. It actually hones in on the exact same features it thought before. So here is the features it thinks are important before the validation set, and here they are after. It only gets more certain that it's the triplet density of states that's predictive. So basically it's saying, I figured out it was the triplet density of states the first time, but I kind of misfit the coefficients on the model. Same thing for this comparison to the T1 energy. So it is only more certain that it is this triplet density of states. In the final step of this, what we wanted to do is say, okay, we learned something, as in we learned that the triplet density of states of a molecule is a fingerprint of how photostable it will be in our experiments. That's kind of cool. How can we exploit that to make further progress? In working very closely with Charles Schroeder and the graduate students in my lab, we tried to come up with a mechanism that could possibly explain why the high energy triplet density of states should be predictive of photostability across this whole region of molecules. It ends up being the solvent. The predictive feature in the triplet density of states was at 4 electron volts. That was the one of the features that was just the sweet spot for predicting if a molecule was stable or not over a long time. If you go in and you look at chlorobenzene's lowest lying triplet state, it sits right smack dab at about 4 to 4.1 electron volts. Lines up perfectly. So the posited mechanism, and this builds off of a lot of literature precedent that we went through, is that if your molecule has energetic triplet states right around the same energy level as where the solvent absorbs or the solvent holds triplets, it is a resonant transfer pathway that basically sensitizes your molecule and accelerates degradation. So we then took this and said, okay, well, if that's the mechanism, then we can trivially boost all of the photostabilities by just switching the solvent so we get rid of this pathway. So we basically go to toluene and decane, purposefully detune this triplet state energy away from 4.4 electron volts, tunes it way up high, and all the photostabilities go up dramatically. This is logarithmic. So the fundamental insight here, there's basically 2 versions. The first version is that the high energy triplet density of states is predictive of photostability, and it ends up being related to solvent. Fine. The more fundamentally important thing here is that we relied on a purely AI Bayesian optimization driven campaign for a problem in which we knew next to nothing about what the answer should be, and we ended up with a useful, productive insight towards our optimization goal that was not just black box optimization, but actually sort of taught us something useful about chemistry. That is the takeaway here that I think is important, should be hopefully important for the folks in the audience and anybody else, is that in these low data regimes, it is really useful to trust these optimization algorithms moving forward. With that, I hope that you've managed to see, the big picture is we want to advance quantum mechanical predictions in soft materials science. I'm a modeler, but there are certain problems that can only ever be addressed with experiment. And if you were to take away, 3 take-home points from this talk, I would propose that they be the following. The first, polymer science, which is traditionally classical physics, needs some amount of quantum mechanics. I'm not saying how much, but it needs some in order to tackle today's emerging problems: sustainability, degradation, electronic property design, synthetic design. The second is, of course, that one fruitful way to try to accelerate these predictions is to work entirely at the coarse-grained resolution. This is the dogma of all coarse-grained modeling in polymer science. But in chemistry, it can be uncomfortable because when you throw out nuclei, that isn't great for chemists. But electronic coarse graining and these approaches can really hold the hope to dramatically accelerating this. And the last point is that while chemistry and polymer science are data scarce by necessity, most fields are data scarce at this point. I really truly believe, as an AI person, that for the immediate future, the state of the art will be pushed by close experimental collaborations between experimentalists and modelers that incorporate AI to basically maximize the efficiency of the experimental campaign. But ultimately, there are just some things that are too challenging for modeling to take on in the immediate future. And so to make progress in something like photostability, you really need this integration. I have a fantastic group. The work that I showed you here was done by a number of folks in the group. They're really, anytime you give a talk, you're talking about your students, you're not talking about what you did. So I really am grateful for them. I've had, as I said, amazing collaborators and mentors in these folks up here on the right, whom I'm incredibly thankful. And the topics of my talk come from a number of areas, or the topics cover a number of funding areas, so I put these up here. But with that, I'm very delighted to take any questions, and thank you for having me. Okay, so I am now running the Q&A. So I have 5 minutes on the clock, so if anybody has questions, please come to the microphones. Or not? Yes.
Hi. Thanks for your talk. So as an experimentalist, but not a lot of, in like AI modeling or anything, how would you recommend somebody get started into AI modeling using experimental data and everything?
Absolutely. Great question. So there are a few important things that have to happen in the field. The first is that chemistry, and I would say ACS in general, has to embrace incorporating data science and ML education into the curriculum. It has to happen. That does not help you right now. The version of this that helps you right now, there are a number of faculty who are producing free, basically, lecture notes and courseworks. If you're interested, just email me, I can send them to you. Okay. But the way that we try to frame these moving forward is like, we want to be as applied as possible, right? While we love the theory nerdery of machine learning, usually you just want scripts that get the job done. And so I can tell you that in the next year or two at max, there's going to be an enormous proliferation of these things on the web that can hopefully help you out. But honestly, just send me an email if you want them now.
Thank you.
Yeah. Kind
Okay. I apologize if this is a naive question, but I'm kind of wondering, do you have an intuition as to when you have done enough hypothesis testing, given that you found the best performer in the lowest data set kind of, I don't know, by chance in this case that you demonstrated? So going forward, when you're using this and trying to generalize it to more properties, when isn't enough?
That is not remotely the naive question. That is the most important question of hypothesis generation. I don't know. It's really tough. So, in any scientific adventure, you are basically, what do you want from the experience? So in this case, our determining factor is, if I find a feature that I can physically rationalize and I can predict photostability with, that is a big accomplishment. So I can guarantee you there are other physical mechanisms governing photostability that we did not uncover. Science has as many questions as you dare to ask. So I don't have a great answer for that, to be perfectly honest. Yeah.
Well, thank you very much, and thank you very much for the talk.
You're welcome.
Hi, thank you for amazing presentation. I was wondering, other than the electronic property predictions in the coarse grain level, is it possible to look into also optical properties? Because you showed liquid crystals, and I'm actually very interested in the color predictions, in terms of what kind of color it would be perceived. But I know that it's like a multi-scale problem because you need to look into ab initio level to get polarizability calculation and all that, but then based on how it assembles, then you want to predict the color. Is it possible to do that?
It is. It's very hard. So actually, we just started venturing into this area, right? So you have to disentangle like the refractive-based color from the absorption-based color, but you can do it. And so again, I think in the next year or two, you will see some papers on how to actually do this. But it's very much, I'm happy to say it's very doable in the near future.
Okay, thank you so much.
Yeah.
Okay, I'm going to have a hard time formulating this question.
I'm going to have a hard time formulating the answer.
Okay. So, AI, computations, they're just tools.
Yeah.
But at the end of the day, it's the people who have the questions and the chemical vision, and we have to use the tools to test their vision and then develop it.
Yeah.
So how do we know that you don't over-rely, because any student who has ever done computational chemistry, including myself, has made the mistake of over-relying on the computer, and you really shouldn't touch the computer until you have a vision and you have a way to know how to use the computer as a tool to test your vision. So how do you know that you're not over-relying and you're using common sense and chemical intuition when you approach these problems?
Excessive self-doubt. I honestly, it's like whenever, especially in the recent times, like in applying AI, just go into it cynical at every moment. That's honestly how I function. And as an AI guy, you just say, okay, this is a challenging thing. I'm resorting to AI because I need help, basically, for some tool. And I'm just not going to trust it. Just like basically my answer is I just generally don't trust things for a while.
So what I would do is probably, I would assume that my results are garbage until I can explain otherwise.
It sounds like you have an answer. Honestly, yeah.
So, great talk. I forgot to compliment you.
Oh, thank you very much.
So I'm going to compliment you now.
Thank you very much. The buzzer is up. Apologies. Feel free to come talk to me afterwards. I'm delighted, but thank you very much again.
Please welcome back to the stage, Dorothy Phillips.
Thank you. Oh, stay. All right.
Thank you, Dr. Jackson, for today's lecture and your devotion to your science and to the ACS. Thank you. Can we have another round of applause? Thank you. This ends the lecture.